Hello, everyone. So this is the session of formal methods. I'm Minxue Pan. I'll be chairing this session. We have 3 talks today, and each talk will have 20 minutes or so, including the question and answering time. And for the audience, if you have questions, you can just put them in the Zoom chat or maybe the Slack channel is fine. And also you can ask questions yourself if you want to. And our first talk is stat-based automata construction for LTI over finite traces. The presenter is Yingying Shi.
Okay. Hello, everyone. My name is Yingying Shi, and the talk I'm going to share with you today is set-based automata construction for LTR over finite traces. This talk will be divided into 4 parts, assuming that you don't have background knowledge. In the first part, I'll give you a quick overview of the preliminaries. After that, I'll show you our approach. In Chapter 3, I will show you our empirical evaluation, including benchmarks and experimental results. In the end, I'll conclude our work. The first concept I want to introduce is linear temporal logic. Linear temporal logic was first introduced into computer science in the 1970s, and since then it has received a lot of interest from many research communities, such as formal verification, software engineering, and artificial intelligence. The standard LTR formulas are interpreted over infinite traces, which are suitable for describing the infinite behaviors of the non-terminating systems. Meanwhile, LTRF, a variant of LTR, are interpreted over finite traces, has raised great interest from the AI communities. The key problem is how to translate the LTR formulas to its equivalent automata. Constructing the NFA, which is non-deterministic finite automata, is sufficient for LTRF satisfiability checking. Constructing the DFA is suitable for LTRF synthesis, and this talk mainly focuses on the NFA and DFA generation from a given LTRF formula. We have known the history of LTRF. Let's move on to its syntax. LTRF formulas are mainly composed of 3 elements, atomic propositions like P1, P2, and so on. Boolean operations like conjunction, union, imply, and negation. Temporal operators like weak next, next, global, future, until, and release. Furthermore, future and global, release and until are dual operators. Then the semantics of LTR formulas are interpreted as follows. A is true if A is true now. Next A is true if A is true in the next state. Weak next is the same as next formula, except that weak next is always true in the last state of a finite trace. Future A is true if A will be true in the future. Global A is true if A will be globally true in the future. A until B is true if A will hold true until B becomes true. A release B. Release is until and release are dual operators. A release B is true if B will hold true until A and B holds, or A never holds. This page shows the definition of finite automata. A is a tuple composed of 5 elements: sigma, S, rho, S0, omega. Sigma is the set of alphabets, S is a set of states. Rho is a transition function. The initial state is said to be S0. Omega is the set of accepting conditions. It should be noted that the accepting conditions distinguish the transition-based automata from the state-based ones. I will give you an example. For example, there is a state-based finite automata in this picture. Sigma is the alphabet set, which is A, B. There are two states in this automata, S0 and S1. The initial state is S0. There are three transitions in this automata. S0 to S0 with a label A, S0 to S1 with a label A, S0 to S1 to itself with a label B. The final state is S1. Here is a definition of transition-based NFA. Given an LTRF formula phi, the corresponding transition-based NFA is defined as a tuple. Sigma is a set of alphabets. L is a literal set. S belongs to CL. Phi is the set of states. CL phi is the set of subformulas of phi. Rho is the transition function. S2 in rho S1 omega means S1 is the current state, omega is a label, and S2 is the next state. S0 equals to phi is the initial state. T belongs to rho is the set of accepting transitions. That's why we define this automata like as a transition-based NFA. Here's the definition of population atoms. For an LTRF formula phi, we define PA phi as follows. And from the definition, we can see that PA phi is the union of if phi, and phi is composed of an atom next, weak next, until or release formula. For example, given a formula phi equals to A and not C and A until B, PA phi equals to A not C and A until B. This page shows the definition of propositional formulas. Given an LTR formula phi, phi p is a propositional atom over PA phi. For example, phi equals to A and not C and A until B. PA phi equals to A not C and A until B. Then phi p equals to A and P1. P1 is a Boolean variable representing the truth value of not C and A until B. Here we come to the definition of next normal form. According to the LTRF semantics, these definitions are quite easy to catch. One thing to notice is that next normal form, which is XNF formula. XNF formulas are composed of only Boolean atoms and next formulas. Now we come to the third section, approach overview. The second section. Before presenting our tour, I will introduce you two excellent tours. Spot and Mona. Spot, the first one is Spot. Spot is the state-of-the-art LTR to Bookie translator. So to construct the NFA, one has to first convert the LTR formula to its equisatisfiable LTR formula, generate the Bookie automata, and then convert the Bookie automata to the NFA. Bookie automata and the NFA share the same syntax. The only difference is that NFA accept the word if there's a round that ends in a final state, while bookie automata accept the word if there's a round that visits final states infinitely often. This is Mona. Mona can translate first-order logic to the equivalent minimal DFA, so one can first convert the RTR formulas to its equivalent first-order logic, and then use Mona to translate the first-order logic to the minimal DFA. Both Spot and Mona utilize BDD techniques to keep the generated automata small. However, constructing the NFA or DFA with Spot and Mona is not efficient. For LTRF, this satisfiability checking. It's too late to do the checking after the whole NFA is generated, since in theory the complexity of LTRF to NFA is exponential. It's even worse for LTRF synthesis, whose solutions relies on the generated DFA, and the complexity of LTRF to DFA is double exponential. So, in fact, both the LTRF satisfiability checking and the LTRF synthesis benefit from the on-the-fly LTRF2 automata construction. And the on-the-fly LTRF2 automata translation only construct the necessary part of the automata for the purpose. Here's our tour. Having the conversion cost from an LTRF formula to XNF is linear to the size of the formula. The formula on the right side of the screen has been converted to XNF. Then an set solver will compute a satisfying assignment A1, which is not C and D. Next, C release D. Analogously, the assignment A2 equals to CD, not next C release D, tells that there's a transition from S0 to S1 with a label C and D. And the new state S1 equals to TT. And we continue the above process until no new state is generated. The red transitions in the TNFA are accepting transitions. To convert a TNFA to its equivalent NFA, one can first create a new state S2 and add the transition into the resulting NFA for every accepting transitions in the TNFA. For example, in the TNFA, S0 to S1 with the label C and D is an accepting transition. So we add a new transition S0 to S2 with the label C and D to the resulting NFA. The final NFA is shown in the right part of the screen. The construction from LTRF to TDFA is analogous. Here's the difference between TNFA and TDFA. For example, in this TDFA, there are two transitions: S0 with S1 with a label A, S0 with S2 with a label B. In fact, A equals to A and B or not B. B equals to B and A or not A. We combine all the states corresponding to the same label to form a new state, which is S0 to S1 and S2 with the label A and B, S0 to S1 with the label A and not B, S0 to S2 with the label B and not A. Here we come to the third section, empirical evaluation. We implemented the on-the-fly construction from LTRF to TNFA using LTAF. Then we compared the performance on the automata construction among three tools, that is, LTAF, Mauna, and Spot. In summary, we collected 600 LTR as LTR formulas as our benchmarks because LTRF and LTR have the same syntax, and we ran each automata on Ubuntu 20.04 with 4 processor cores, 3.2 GHz, and 8 GB of RAM. The timeout was set to be 120 seconds for each tested formula. Instances that cannot generate the corresponding automata within timeout will receive a penalty of 120 seconds. Table 1 shows the results for LTRF2 automata translation on the LTR as LTRF formulas, and the first column categorizes our benchmarks according to the number of states. The last row summarizes the number of formulas for which each tool generates automata successfully. And I'll select the data row 2 for explanation. There are 36 instances on which Mauna failed to complete the automata construction. Meanwhile, Spot generated the corresponding automata with each having 4 states, and our tool finished the automata construction with 2 states for each automata. This is the last number among all 3 tools. Table 2 shows the experimental results for our comparison on the number of transitions among 3 tools. Here we select the data of row 2 for explanation. In these 73 instances, each tool successfully generated the corresponding automata. The number of transitions of each automata is in the range of 1 to 500. Finally, we present the time cost for each tool. Spot spent the least to complete the benchmarks, followed by LTAF and Mauna. Spot is highly optimized after decades of development, so it's not surprised to see that Spot outperforms other tools. And our tool, LTAF, is just a prototype, and many improvements can be applied in the future. Here comes the last section. Our tool introduced in this talk differs from the other 2 tools as follows. The translations are straightforward without involving any intermediate process. In addition to that, the resulting automata of our approach are transition-based, which has been shown more efficient than the state-based ones. Most importantly, our tool leverages the set instead of the BDD techniques, which makes it more useful for on-the-fly applications such as planning. Thank you for listening.
Okay, thank Yingying for the presentation. We are a little bit running out of time, so we can take one question. Okay, so I have a question. So as we know that the LTR formulas are often used as specification in model checking, and they are often transformed into automata to be checked against the system model. So is it possible to check the transition-based model here to a system model that use the state-based style?
In this talk, we use the transition-based automata.
Yes, I mean, if you have properties in transitions, can you check the model against a system, another model which properties are in states?
Yes.
Okay. Thank you, Ying, for the presentation. And now we move to the next one. The next one is fault diagnosis of simplified fault trees using state transition diagrams presented by Mingyue Jiao. We have 17 minutes for the presentation. Yingying, could you close the screen sharing? Mingyue, you can begin now.
Hello everyone, my name is Jiao Mingyue. I'm from East China Normal University. The topic of my presentation is fault diagnosis of simplified fault trees using state transition diagrams. My presentation will include these three main parts. First, the introduction of our research. Second, the methodology we have proposed in this paper. And the last, a case study. In the first part, I first want to introduce the background of my research. Aerospace systems are classified as safety critical systems in which a failure could lead to significant property damage or loss of life. Reliability is one of the main research directions in the aerospace field, and fault tree analysis is a reliability analysis technique and widely used to analyze complicated systems, including aerospace systems. Fault tree was developed for the U.S. Air Force for use with Minuteman missile system to interconnect all contributory events and conditions that lead to an identified undesirable top event. Fault tree analysis is detective in answers, meaning that the analysis starts from the top event and moves toward the leaves to determine the root causes. At present, the related works of fault tree mainly focus on reliability analysis, which mainly includes qualitative and quantitative analysis. At the same time, there are many researches on the simplification and false diagnosis of fault tree. For simplifying the fault tree, one of the widely used traditional approaches is based on program package for evaluation of fault trees to prune the redundant events and logic gates without changing the logical structure. It mainly focuses on repetitive basic events and the most common AND gates and OR gates. Since the representative logic of fault tree can be described with Boolean algebra, Some studies apply the reduction rules of Boolean algebra to simplify the force tree, but often change their original logic structure. For the force tree-based force diagnosis, it is mainly combined with other technologies, since using force tree analysis to diagnose the force is actually to find the critical basic events that cause the top event. The most related studies focus on the basic events. To facilitate applications in certain specific systems, some other studies treat basic events and intermediate events as the same elements in other technologies. In addition, many related researches on force tree-based force diagnosis sought failure events or failure combinations so as to detect them in turn until a critical force is found. Through the study and research of the above related works, we found some problems that still need improvement. Firstly, for these studies, they all do not pay much attention to those unreachable subtrees. In the force tree, basic events are initiating or basic force that do not require any further development or expansion. Because of the concurrency of certain basic events and their inverse events, there may be logical contradiction in the force tree, making related subtrees unreachable. As the complexity of array-space systems increases, NOT gates and some spatial gates may also be used in force trees. And there are inverse events in NOT gates and spatial exclusive OR gates. Therefore, unreachable subtrees may appear in the force tree and need to be detected from force tree analysis. Secondly, an intermediate event in the force tree is a force that is caused by the location combinations of other events occurring further down the tree. When an intermediate event does not occur, there is no need to detect the basic events below it, which can avoid the unnecessary operations. Therefore, it is unreasonable to deal with basic events and intermediate events equally. Finally, due to the complexity and diversity of aerospace systems, a top event may be caused by multiple failure combinations. In this case, previous force diagnosis methods need to detect all elements in the sorting, which will increase the workload. To address the aforementioned issues, we propose a new methodology for simplifying the force tree and then performing force diagnosis. By transforming the force tree into a state transition diagram, we perform a satisfiability analysis on subtrees to simplify the force tree. Afterward, we treat basic events and intermediate events differently to optimize the force tree-based force diagnosis process. Therefore, our primary contributions can be summarized as follows. For simplifying the force tree, we perform a SAT analysis on the formula conjunctive normal form, which is obtained from the STD of the subtree, and the SAT analysis judges the reachability of the subtree on the basis of returning the original logical structure of the force tree. During the process of force tree-based force diagnosis, we perform different treatments on basic events and intermediate events. This advises dispensable operations to detect critical force and define multiple failure combinations. Our method can be applied to various fields that want to use force trees for force analysis and diagnosis. especially in the aerospace field. In the second part, I will introduce the proposed methodology in detail. Firstly, I want to describe the transformation of force trees to state transition diagram. According to the nature of force trees and state transition diagrams and our needs, we formally define them in the paper as shown in the pictures. Then, I will describe the transformation process in 3 steps. In the first step, we define the transformation rules for 3 standard logic gates: AND gate, OR gate, and NOT gate, and we formally describe the transformation process. During the above transformations, where there is a nested subtree, we need to continue the transformation according to the above rules. And in order to rigorously define the rules, we make some replacements and supplementary descriptions as shown in the slide. Finally, we make some modifications to the STD of the final force tree. The standard force tree contains the above 3 types of gates. However, force trees may also contain some special gates to describe more complex failure conditions. Special gates, mainly including XOR gates, inhibit gates, and voting gates, can be expressed by combinations of gates in the standard force tree and then transformed into STDs through the above method. Fig 2 and Fig 3 on the slide shows some examples of special gates. After obtaining the STD of the force tree, we perform SAT analysis on certain subtrees to simplify the force tree. This part is also divided into 3 parts. In order to search and delete unreachable and redundant subtrees, we first select some subtrees that meet certain conditions to shrink the search scope. The unreachable subtree is essentially caused by the logical contradiction between basic events and their inverse events. Therefore, we perform SAT analysis on subtrees containing basic events and their inverse events without analyzing all the subtrees. In a force tree, if there is any minimum subtree that satisfies these conditions, as shown on the slide, the subtree may be unreachable and needs SAT analysis. We used the transformed STD to obtain the CNF formulas which represent the selected subtrees using SAT analysis. SAT analysis is to determine whether there is a true value assignment for a given CNF formula. Therefore, we can perform SAT analysis on the CNF formula representing the subtree structure. If the result is unsatisfiable, it means that the subtree is unreachable. Organism 1 describes the process, which takes an STD transformed from a subtree as input. The general idea of organism 1 is to connect all formulas of state or sub-STDs in the STD by connective end of proper reasonable logic. The formula of a state is itself, and the formula of a sub-STD led by an organizing state is obtained using organism 2. It should be pointed out that on line 20 of organism 2, if the obtained Q is an unstandard formula, in disjunctive normal form. It needs to be convened according to the distribution law. This is an example of more than two steps. The CNF formula of the subtree is the union of more formulas on the rightmost side. In the last step, we use the SAT solver to perform SAT analysis for determining whether a CNF formula is satisfiable. For the subtree corresponding to an unsatisfiable CNF formula, we delete its related content to simply the first tree and generate a new STD. After simplifying the first tree, we can still use the STD to perform some effective first tree analysis and false diagnosis. The STD transformed from the first tree covers all paths leading to the failure of the top event, which are false paths. These obtained false paths include states and transition conditions, which are transformed from basic events and intermediate events separately. The basic event set in a false path is a failure combination or failure event for the top event. And the number of basic events in a false path can help us evaluate the false dips that the top event can withstand. As an important method of false tree analysis, minimal cut size provide critical information about vulnerabilities of a system. According to the set of false paths obtained above, the basic event set in each false path can be considered as a cut set. The probability of a false path is the probability that all basic events in it occur. Analyzing the probability of these false paths cannot help us find weak parts in the design phase, but also filter us to diagnose after failure. And the top event probability is an important index for assigning reliability. According to the failures on the slide, we can calculate this data in turn. After failure of the top event, we use the set of false paths and their calculated probability to perform false diagnosis. First, we need to sort all the false paths according to their probability from high to low. Then we perform false diagnosis on the sorted path following the process. In this process, we do not need to detect the basic events in a path when the corresponding intermediate events do not all occur. The basic event sets in the path we selected are the critical failure combinations that cause the top event failure. Finally, we choose a case study in the field of aerospace to illustrate our methodology. Taking the failure of satellite ground station receiving system as the top event, the first tree is shown in the slide. And the false descriptions and prior failure rates of events are displayed in the slide. First, we obtain the STD of the first tree and we found the rightmost subtree is unreachable. Then we perform a series of analyses and calculations on the simplified first tree to get some important information. In the end, we diagnose the false path. The table shows the false path and the corresponding basic events that need to be detected when different intermediate events occur during the diagnosis. As we can see from the table, in the best case 3 and 7, we only need to detect one basic event. In the worst case 18, we need to detect all basic events in all paths, which is the same as the diagnosis method of some researches. In other words, our method will have better results on average cases. That's all for my presentation. Thank you.
Thanks, Mingyue, for the presentation. Now we can take questions. Okay, so I have a question. So have you compared to other approaches to check how does your path pruning and path simplification methods improve the efficiency of your approach? Mingyue, are you there?
I'm here.
Okay, so have you?
Please.
So have you conducted any experiments to see how your path simplification and path pruning improve your overall efficiency?
By pruning the redundant subtrees of the fourth tree to improve the efficiencies.
Okay, thanks for the presentation again. And now we move to the last talk, lemma weakening for state machine invariant proofs.
Yes, I'm here.
Okay.
Hello, everyone.
Okay, Tran, we can begin now.
Yeah. I hope that you can hear me. If you think that I should speak louder, then please let me know.
Okay.
Yeah.
It sounds fine now.
Okay.
Yeah, it sounds fine now.
Let me
So
share my screen.
Share the screen, please.
Yeah, can you see it now?
Yes, yes.
Okay, so let's start. Once again, hello everyone. My name is Duong. I'm from Jian in Japan. Today I give a presentation for our paper, lemma weakening for state machine invariant proof. Here's the outline of my presentation. First of all, I will give a small example to describe about lemma conjecture problem. Considering a list of elements, here we define a vertical bar Gplan for the constructor of the list, len is an empty list, and we also define us as a concatenation function between two lists. Then we also define the reverse function of a list by two rules R1 and R2, as shown in the slide. We have a theorem such as revert of a list L will become L itself. To prove this theorem, this claim, one possible way we can do it by using induction proof. So that we will apply induction on variable L. Accordingly, there's two main steps we need to tackle. In the base case, revert of len will become len itself by 2 times apply rule R1. Next, we move to the induction step. In this step, we suppose we have induction hypothesis. Revert of L will become L. And we want to show that the theorem also true with E vertical bar L prime. By applying rule R2, we can rewrite the left-hand side of this equation, become like this, as shown in the slide. But in this point, we cannot apply neither rule R1 or rule R2 anymore. Then we need to construct or conjecture a lemma to complete our proof. The most straightforward lemma we can conjecture is by just keep the last equation become to exactly what we expected here. However, during the proof of lemma 1, it requires to conjecture another lemma L2. If we try to prove L2, then it also requires to conjecture another lemma L3. So I suppose that. So what is the problem here? If we continue to try to conjecture in this way, then it seems that we can never complete our proof. When C is the same or the difference between L1 and L2, we can see that they are almost the same. The difference is only highlight in the yellow color. You can see the slide. So what we need to do here is suggest us that we should make the more general version of L1 or L2. Such lemma we conjecture L0 here. L0 will be stronger than both L1 and L2. Or we can say that L0 is a generalized version of L1 and L2. Stronger and weaker between two predicates. Here we can understand as follows. If we have predicate P imply predicate Q, then you can say that P is stronger than Q or Q is weaker than P. So in general, if we want to prove a state predicate P is an invariant of a state machine S, then there are two steps we need to conduct. In the first step, we need to show that P holds in arbitrary initial state elite, which is represented by the left-hand side of the figure. And in the second step, we should to show that if P holds in a state S, then it also should hold in its successor state S prime of S, as shown in the right-hand side of the figure. And here we call S to S prime a transaction instant. However, during the proof, there often exists a case such that the transaction instant do not preserve P. This means that P holds in the short state epsilon, but it does not hold in the successor state epsilon prime. It's represented by the figure A here. Here we use the circle to represent for the set such that delta P is represent the set of all state S in which the predicate P is satisfied. In the current slide, we use the blue circle to represent the set. It's different with from the previous one. We use the cycle in the green color to represent the state. So one possible way to get out of this situation is by finding PSTR such that PSTR is stronger than P, and PSTR do not hold in the short state epsilon. Then we can easily to see that this implication will become true. Our remaining task is we need to prove PSTR invariant of S. If we can do so, we can conclude that P also an invariant of S. So in general, to prove a state predicate P an invariant of S, we need to find an inductive invariant Q such that Q implies P. Normally, Q is the form of the conjunction of P, Q1 to Qn. Then we call that Q1, Q2 to Qn the lemma of the proof that P is invariant of S. However, the problem is during the formal verification, we do not know Q1 to Qn in advance, but we need to conjecture some gradual needs. When we have conjecture up to the lemma Qk, we do not know how many more lemma we need to conjecture to complete our proof. At the beginning, I have already shown an example to demonstrate that the correct lemma L0 is only constructed by applying strengthening on the straightforward candidate lemma. Our paper propose another way to get out the transaction instant epsilon to epsilon prime, as I described before. Here we try to find a predicate PWK such that PWK is weaker than P and PWK hold in the successor state epsilon prime. It's represented by the figure C here is the middle. If we can do so, then again this implication also become true. However, in this way, even though we can prove that PWK is an invariant of S, we cannot conclude that P also an invariant of S. That's why this technique seems not useful to prove P is an invariant of S. However, it's useful for some lemma Qi. such as this lemma is the proof of P. So here we call strengthening lemma QIS, lemma strengthening, and weakening lemma QIS, lemma weakening. At the beginning, I have already shown the power of lemma strengthening technique Q, and in the remaining part, I will show about the power of lemma weakening technique Q by the formal verification of MCS protocol. I will move to this section right now. MCS protocol near mutual exclusion protocol. Variant of it were used in Java virtual machine. It implies that MCS is not simple. It's not kind of laboratory protocol. The current slide shows the pseudocode of MCS for equal set P join this protocol. Suppose that a process located at one of 14 locations, IS, L1 to L12. Equal set P has three local variables, like P refer to the like process in the virtual queue. Breadth P refer to the predecessor process in the virtual queue. Look P Boolean value is only true or false. Zlog here is a global variable. Basically, it points to the last process attacked in the virtual queue. The algorithm used to automate function as shown on the right hand side. Initially, each process located as IS, like breadth and zlog reload, and look P false. In this slide, we graphically show the chain of the state when process P move to L2, L3 from L2. As you can see in the short state, epsilon, the portion Q only consider Q and R. Then in the successor state, when process P move to L3 from L2, it means that this statement will be executed. Then P will be attacked into the virtual queue, and the log change from Q to P. MCS is a mutual exclusion protocol. Then it should satisfy the mutual exclusion property. The property says that at any given time, there is more one process located at the critical section. To prove that MCS enjoys this property, we firstly we use cafe obj, which is a specification language to formalize MCS, and then we represent the property by the mutex predicate as shown in the slide. We will apply structure induction to prove that mutex predicate how we own reachable state S. So during the proof of mutex, we need to conjecture 7 more lemma in 1, in 2, 2 in 7. In short, without the use of lemma weakening, we have stuck to complete our proof until that before we finding the way of using lemma weakening, we so stuck to complete our proof. So I will describe 2 case in which it shows the power of lemma weakening technique Q. In the first case, during the proof of mutex, we use a lemma in 4 as shown here. However, from the beginning, initially we come up with in 4.0 instead of in 4. The difference between in 4.0 and in 4 are highlighted by the green, yellow, and pink color. We can see that in 4 is weaker than in 4.0 or in 4.0 is stronger than in 4. That's why we believe that strong in 4 to make in 4.0 is a correct way to complete our verification, as shown in the beginning example. Even though we cannot complete the proof of in 4.0, but we can do so with in 4. So what is the reason why the proof of in40 is so hard? During the proof of in40, it has a transaction instant epsilon 40 to epsilon 40 prime, and this transaction instant the lost preserve in40. Then we need the conjecture in for 1. And again, during the proof of in for 1, it exceeds the transaction instant epsilon for 1 to epsilon for 1 prime. Such that this transaction instant does not preserve in for 1. The state epsilon for 1 is represented by figure A here. Again, we conjecture in for 2 to get out of this transaction instant. But during the proof of in for 2, it exceeds it has again a transaction instant epsilon for 2 to epsilon for 2 prime, and this transaction instant the loss preserve in for 2. The state epsilon for 2 is represented by figure B here. And again, we conjecture in for 3, and it also has some K. We need to conjecture another lemma. So the situation we need to dealing with here is somewhat similar with the example at the beginning I have presented. It suggests that we should make a stronger lemma that is stronger and more general than exact lemma or invariant here. However, we could not do so because you see every time a new lemma conjecture it has one more parameter. You see, and you can see by the figure here, the difference between figure A and figure B is only one process C R here is inserted into the middle. Even though R in figure A should be correspond to a T in figure B, and the difference between figure B and figure C and more process T here is inserted into the middle. So in this way, we could not find the most strongest lemma that is stronger than all of the lemma here. That's why we cannot complete the proof of in40. But if we make this more weaker, a little bit weaker as in4, then we can complete our proof. That's the first case. In the second case, during the proof of mutex, we also use a lemma in5 as shown in the slide. Again, from the beginning, we come up with in5 0 instead of in5. The difference between in5 and in5 0 is only in in5 0 we omit this equation. P should be different from Q. Because in both in5 or in5 0 we have legs of Q is P, you see here. Then we believe that P is different from Q is unnecessary condition because we believe that leg of P cannot be P itself. However, there is a big difference between the proof of in5 and in5 0. Why the proof of in5, which is the weaker version, we require only in 3, and the proof of in 3 only require in5. It means that we only need one more lemma to complete the proof of in5. Why the proof of in5 0, which is a more stronger version, it requires in total 9 more lemma. And two of them you can see as shown in the slide. Even though it's so obvious or trivial, but the proof of this is not simple. So that's the 2 case I show the power of lemma reckoning technique Q. In our paper, we have formally verified that MCS protocol enjoys the mutual exclusion property. Our proof is based on writing proof score and executing them with cafe obj, which means that our proof is 100% mechanic. It's not kind of a hand or paper and pen proof. Actually, we have started in several months until we finding the way to using lemma reckoning to complete our verification. One piece of our future work should be we should conduct a more case study to determine when and how we should use lemma reckoning, and we should find a systematic way to to know just when we should use this technique in formal verification. So that's all for my presentation. Thank you for your attention. I'm open to any question from you.
Thanks, Duong, for the presentation. Since we are running out of time, we will only take one question.
I see.
Anybody has a question? Okay, I have one question. So although it is in your future work, I would like to know if you have any insight about when we should use lemma weakening.
Actually, to come up with this idea, to be honest, so far, we did not come up with the systematic way to use lemma weakening. However, we plan to developing a tool so that we can, for the very naive idea is that we, for every lemma candidate, then we try to make it a little bit weaker, and then that is if it can help us to complete our verification. It means that it can be proved in a simple. That's why because in this way, there are many lemma candidates that is weaker than the current lemma. Then we need to develop a tool to do this automatically instead of proof by writing manually. You know.
Okay.
That's a very naive idea.
Okay, so that will be all for this session, and let's thank all the presenters again.
Okay, thank you for listening.
Thank you.